Okay, we're going to take a look now at a little application. We kind of already started actually at the very beginning of the course with essentially this, but we want to look at the integration. And in particular, we want to look at the integral of the rate of change, which turns out to be the net change of the quantity whose rate of change is given in the integral. So let's explain what's going on there. Let's start with a simple example. Suppose we have water flowing into a large empty tank. And we know the rate that the water is flowing in, we'll call that R, and that's say 10 gallons per minute. Okay, so if it's flowing in at 10 gallons per minute, how much water is in the tank in half an hour? Well, the quantity of water is simply going to be that flow rate times the elapsed time. Right? And so the flow rate we have is 10 gallons per minute. Now units are going to be important here, right? 10 gallons per minute times what? The elapsed time. Well, the elapsed time was half an hour. Are we going to put half an hour here? Notice this is 10 gallons per what? Minutes? No, we need the correct units in minutes. So half an hour, of course, is 30 minutes. And that's the time that we need to put in here. Notice our minutes cancel out and we're just left with gallons. 10 times 30 is 300 gallons. Okay, so that's a pretty piece of cake, right? The quantity, the rate of change is constant here, okay, which makes this problem really simple, right? Constant rate of change times the elapsed time gives us the total net change in the tank, right? 300 gallons will be put into the tank after 30 minutes. Graphically, you know, if we look at it, here's our flow rate here in gallons per minute again. And then our time here in minutes, right? And the flow rate is constant at 10 gallons per minute, right? And so from 0 to 30 minutes, we can think of this geometrically then as basically the area under this curve, if you will, or line, right? Which is 30 times 10, 300 gallons here. And the units, gallons per minute times minutes gives us gallons. And so what does this mean? Essentially, we can integrate what? What is this? What function is this? It's the rate of change, the flow rate. We integrate the rate of change, right? And we will get the net change over that, in this case, time interval. You say, well, why would we need to do that, right? We just multiply. Well, the idea is that the flow rate typically is maybe not constant. And so what happens if your flow rate instead is variable? So over time, the flow rate is very low. It begins to build up, maybe peaks at about 20 minutes, and then it begins to taper off again. So now we're talking about, right, in 30 minutes, the amount of water in the tank will be the area under this curve. Right? And there's so many applications where we want that change in quantity, and so you're integrating the rate of change. And so this is an application, obviously, of the definite integral. And so this is now written this way, right? The net change in the quantity of some function over a time interval, say t1 to t2, is given by this integral. Notice what we're integrating here. That is s with a little tick mark. That's the prime. That's the derivative of the function s, which is what? The derivative is what? Literally the rate of change of the function. Right? And it's equal to, obviously, s of t2 minus s of t1, since, the antiderivative of s prime is s. But what is this? S of t2 minus s of t1. This is the quantity of the function at time 2, and this is the quantity of the function at time 2. So the difference will be the net change in the quantity, right? So the quantity on the left is the integral of the rate of change, right? The integral of the rate of change of s, and the quantity on the right is the net change in s over that interval. And so that's the application. So let's look at some examples now. We'll look at a variable flow rate, right? Water flows in an empty tank at a rate of 100 minus 3t squared gallons per hour. What is the quantity of water in the tank after 5 hours? So let's let our s of t function, in this case, be the amount of water. And what's our water quantity measured in? We want to do gallons. Let's make sure of that. In the tank at time t. Right, time t. Of course, t, what units do we want to have for t? I think we're gallons per hour, so let's keep that in hours, right? So I know, therefore, what's S prime of t? That's the rate of change of the water in the tank. And so since the water's flowing into the empty tank at this rate, there's S prime of t. Further, we know what is S of 0. Do we know what S of 0 is? What's S again? It's the amount of water in the tank. Initially, right, times 0, what do we know? Well, we're told that the tank is what? Empty. If there's empty, that means there's no water in it, and so there's 0 gallons of water in it. And the question then, what is S of 5? Don't know. But the integration will help out here. The definite integral will help out. So the net change over the first 5 seconds in the amount of water in the tank is given by this, right? Find out the difference. Of course, S of 0 in this case is 0. But in general, you want to write this out in case S of 0 is, check the problem out. There might be some actual quantity of water in the tank, because this, again, this integral that we're getting now from time 1 to time 2, of course, our time 1 is 0, our time 2 is 5, so from 0 to 5 of what? The integral of the rate of change, right? S prime of t. So the integral of the rate of change. Integral of the rate of change is the net change. There it is. So I can solve this problem using the fundamental theorem of calculus. Part 1, what's the antiderivative here? Antiderivative of 100 is 100t. Antiderivative of 3t squared is just t cubed. And I'm going to evaluate that at 5 and at 0. So I get 100 times 5 minus 5 cubed minus what? Well, 0. Right? If I plug in 0 for t, I get 0 there. And so this is 100 times 5 is 500. 5 cubed is 125. So 500 minus 125 is 375. Our units are gallons. Okay. And since S of 0 we know is equal to 0, we can now answer the question that S of 5 is 375 gallons. So that's the amount of water in the tank after 5 hours. After 5 hours. Okay. Now read the problem carefully, because as I said, this tank was empty. You want to be careful to take into account that you look at the net change. And you have to read the question. Here they're asking for the quantity of water in the tank. So be careful. They might be asking for the actual net change in water over that time, which would just be this difference. Okay. So the integral will give you that net change. If you're trying to find the amount of water in the tank, then you're going to have to you'll find this net change, but you're going to have to add to that what was initially in the tank. Okay. Let's do another example. Factory produces automobiles at a rate of this cars per day, t days after a new manufacturing process is installed. So how many cars were produced from the beginning of day 2 to the end of day 6 after this new process is installed? Okay. So let's take a look at this again. We're going to call our function. We're looking at S of t. What? We're going to be looking at what's the quantity? The number of cars, right, produced. So we'll look at the number of automobiles or cars produced, right? T days after new process installed. Okay, after new process installed. Okay, so then of course S prime of t, the rate of change, is what? Given here. This is the rate that the cars are produced. This many cars per day. Cars per day. And so question is, how many cars were produced from the beginning of day 2 to the end of day 6? Now here you got to be a little careful. Okay. Tell me something about what is S of 1. What would that tell me, S of 1? T is the number of days after the new process is installed. Okay. So S of 1 would be how many cars, right, were produced 1 day after the new process was installed. Okay, number of new cars produced 1 day after the new process was installed. Okay, looking for the beginning of day 2. So what about S of 1.5? That's how many cars were produced, what, 1.5 days afterwards, right? 1.5 days afterwards. Okay, but day 1, right, is ending, right? By now we're into what? 1.5. We're into day 2. In fact, this is halfway through day 2, right? Halfway through day 2. So think about it. Let's go in this way. S of a half, right? That would be, you know, halfway through the first day, right? How many cars were produced halfway through the first day, roughly? This would be at the first day. So, beginning of the second day. Where do we need to start from? Do we need to start at 2? You know, S of 2. Do we need to start with T equal 2 days? No, because S of 2, we would be forgetting of it. We would be starting actually with day 3, because S of 2 is everything produced up to day 2. So what I'm getting at is, what I'm interested in is the net change for here. This is the beginning of day 2 to the end of day 6. I want to look at S of 6 minus S of 1. That's going to be the net change. All right, beginning of day 2, right, starts right after 1, right? So this is S of 6 would be, let's find all the cars that were produced in the first 6 days, right? In the first 6 days, okay? And this would sort of take away the number of cars produced in the first day. So what's that going to leave? Days what? 2 through 6. Okay, so it's a little tricky there setting that up. You got to give that a little thought. So there's our limits of integration. The integral of the rate of change. So we'll put the rate of change in here. So now we can calculate this. In this case, notice we're just looking for the net change. This is what we're looking for. This is the net change. This is how many cars were produced in that time frame, right here. So this integral will give us our answer. What is the antiderivative here? 20t plus, we're going to do what? T cubed over 3, 6/3 is 2, t cubed. Just double check if I take the derivative, I get back to 6t cubed. And then I have what antiderivative t is going to be 1/2 t squared. So there's our antiderivative. Evaluated at 6, and I subtracted evaluated at 1, which is, I'm just going to plug in 1 for t, that'll give me 20 plus 2 minus 1/2. Okay, I'll let you go through the lovely number crunching there, right? Dot, 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 you can fill that in, and you should be getting 512.5. Of course, what are our units? What are we talking about here? 512.5 what? Cars. Okay, right, cars. So we got half a car. I guess maybe, you know, we shut down the processor right at the end of the day. We got 1/2 a car done. Okay, still an assembly line or something. Okay, but again, this is the idea behind the integral of the rate of change being the net change. So this is the approximate answer that we're looking for. Okay, So in the next video, we're going to take a look at the difference between, for object undergoing linear motion, the difference between the distance traveled and the displacement. We'll do that next.